Hello, my name is Ericlopen, and I'm here with my partner, Uriel Trujillo.
Hi.
We've created a MATLAB program that calculates the position, the velocity, and the acceleration of a moving object. To do that, we need a video recorded from a static camera, the focal length of the camera, a moving object, and the dimensions of the object.
Correct. The program works in two ways, a 2D and the 3D way. 2D is that we can assume that all the movement, velocity, position, and acceleration is contained in a vertical plane perpendicular to the camera. And 3D is the ball is free moving. Okay, now let's run the code and see the final results. The first video is the most basic one. It's a ball in front of a white background.
Now we can see it's just part of the code, it's running. We can see some images, it's like a video, but actually they are images. At the end we will be able to see the videos. This is the final result. And now we've got the graphs.
Okay, this is the position, velocity, acceleration, and all in one. Well, we can see the position of the gradient center in red, velocity in blue, and acceleration in green. Well, now it seems to be okay. We can note that
the path it's right. It
right.
Seems right. We have a very big acceleration in
the moment
the bounce, yeah. And all the rest of the acceleration are almost vertical downside. There are a little bit deviations like here. Well, it's due to errors, measures. Well,
okay, it's not scaled. I mean, this arrow can be so big, but it doesn't correspond to the number.
Yeah, obviously we have scale factors to do it visible. Now we are going to show you which is the final result, well, the acceleration, the velocity, and the position. And here it's the final result. We can see in a fast movement. Now we're going to do slowly. For example, we can see, as we've seen before in the graphs, all the position, right? This is quite clear. We've got here the center of the gravity, the acceleration, and the velocity.
Well, the numbers, so the magnitude of the velocity and acceleration is saved in a note file.
Yeah, right. And we can later study them, watch them, and whatever we want. Okay, now we're going to proceed with the explanation of the code and the next videos. Now we've seen what the program does. Let's see how does it work. First of all, we have to read the video, and then we have to use our main function, study of movement. We have to know that this program is based on frame subtraction. Our main function is this one. We can get some parameters like frames per second and the time frame. And the first thing that we have to do is get a structure called move, where inside we have an RGB and grayscaled matrices.
Okay, we deal with grayscale because RGB is to information. So, as you said, Eric, our program is based in frame subtraction. So we need a background, a common background that we get in the function getBackground. This function takes a frame and subtracts another, and takes the unchanged region and fills the changed region with a third frame. So this way we can get a background. The following thing is detect the ball. This function takes each frame, subtracts the background, then we have a region change that is the ball and noise, and that we want to remove. We remove it, but we want to be sure that what we take is the ball. So we have to follow some criteria, like we have to take the more changing area, and it has to be bigger of a parameter. A minimum number of pixels. Okay, this function returns a logical matrix which is the area, the region of the ball.
Now, with this logical matrix, we can get the CG using the function getCG that uses a function of the toolbox image called region props. We can also get the diameter in each frame using the function getDiameter that also use the
function region props.
Yeah, exactly. But this diameter is actually the mean diameter of each all the frames. Here we use this code when there's no ball in the image, so the position is empty.
Okay, we go to the case 1, which is the two-dimensional. And the next thing we want to know is the conversion pixels to meters. We know it with the function get pixels to meter. As we know the diameter in pixels and the real one, we can get the factor pixels to meters. Now we're going to get the velocity. To do that, the program subtracts the next position minus the current one and divides by the time frame. For acceleration, computes it subtracting the current velocity minus the previous one and dividing by the time frame.
Now we have the position, the velocity, and the acceleration. We create the graphs on the video using this function. We have 3 different videos. The first one, as you've seen before, is the subtraction, the second one is the detection, and the third one is the final solution. Now that we have seen how the code works, let's verify it. To do that, we're going to use the next video, which is a free fall. As we can calculate the velocity at each time, we can compare it with the analytic solution. Okay, now let's wait till it compilates. Okay, as we've seen before, we are gonna watch the subtraction video, the detection video, and the final video. We are gonna get all the graphs of the position, velocity, and acceleration. And finally, we're gonna get the graph that we are looking for, where we can compare our results, experimental, with the analytic ones. See? Okay. Here it is. Yeah, it works.
Okay, so here we have the, well, in blue the analytical solution and in red the experimental solution. We can see some errors that we think it came from the resistance of the air and that it's not a two-dimensional movement. So it has a velocity in the z direction.
That we are not considering.
Exactly. So the diameter changed.
But I think that we can confirm at least that our code works.
Oh, it seems a little bit to the reality.
Yeah, exactly. Right.
Okay, now let's see another example of two-dimensional movement. Let's run the code. Thinking. Okay.
We're gonna see as before the subtraction. You can see here the noise.
Yeah. In this video has some problems due to the.
You can see the diameter is not constant. That's why we use the mean diameter.
The ball is slow. Is small and.
It's quite far. Yeah, it's quite far.
It's quite far, and there's some shadows.
But well. Okay, let's see the graphs.
Wow.
Okay, these ones.
Well, here we have the graph, the position, velocity, and acceleration.
We can see the trajectory of the ball.
We can check that the acceleration is in the moment that the ball bounces to the wall and the table.
Yeah, they are maximum. And well, like the other videos, I think it's a good result. Yeah.
Well, maybe you can observe that sometimes the acceleration vector.
You make strange things like.
Yeah, this is because the center of gravity is not always
in the same place. Yeah.
In the real center of gravity. because of shadows and well, and this is multiplied by a scale factor to see it clearly, and
it makes the strange things. Yeah.
Exactly.
Okay, right. Now we're going to see the final video. Okay, but first, it is a 3D case.
Yeah.
So first we have to say how does it work. Okay, so we came here, which is our function.
Well,
everything is the same.
The main difference is that we have another component.
We can see it here if it's empty because there's no ball.
Okay.
So it's here, the case 0.
Well, we compute the distance. Well, because we know the original diameter of the real.
Yeah, which is this value here.
Yes, and we know the distance of one frame.
Yeah, exactly. So this is the distance of the frame, and this is the diameter in pixels of that picture.
Yes, and knowing the focal length and by trigonometry.
Yeah, we can. Yeah, exactly. It's that. We can get with this function get prof. We can get which is the distance from the camera to the object, and we can get also the pixels to
exactly
meters because we know this.
Okay, it's important to note that in the 2D case we have 1 pix to meters, and now in each position it's a pix to meter different.
Yeah, exactly. And finally we have exactly the same that we've done in the 2D case. And in the make video we're gonna do the graph, just that instead of 2D you're gonna be in 3Ds.
Well, let's see how it works.
Yeah. Just continue. Okay, it's exactly the same we've done before.
Whoa!
Subtraction.
What? Super cool.
The detection, and the final.
Well, this is Eric's room.
Yeah, it's quite it's quite messy. Okay, well, we have a lot of graphs. We're gonna talk of each one. Okay, here, this is the graph where we have the velocity, the acceleration, and the point. Okay, it's quite real. We can just move it. Yeah, right? Yeah. We can go up, down. Okay, we can see, for example, this is the XE plane. It's quite well. It's what we told before. These changes are because of the change of the position center, right?
Right.
Then we can see the accelerations, the velocities. Right. It's a little bit difficult to understand. As we can see here, it seems that it goes down and then goes up. Well, this is because we are calculating the distance
to the camera.
So,
not the distance to the floor.
Exactly. So we want to know the distance to the floor. We should have to subtract.
To turn our heads down.
Yeah. And to subtract the total height to this height. So let's see another graphs. Okay, here this is acceleration. Well, it's a little bit messy.
It's strange.
Yeah, but it's almost the same. We have to say that this method is not very exactly because diameters change a lot, so it's difficult to get the real velocity. Here we have the velocity. Okay, again.
Yeah, in the 2D case,
it's more easier.
It's more easy because
more accurate. Yeah, sure.
Yeah.
This is the center of gravity. Okay, it makes a little bit of strange things, but just because of the change of the diameter.
Yeah, due to the light.
We can see the video. Okay, let's see. This is our moment where we know the distance to the object and the diameter. Okay, because we know the distance from the camera to the floor. We can see that the diameter increase, so it's going up, and it decrease, it's going down. Okay, well, this is just videos that we've seen before. And well, this is how it works. Yeah, that is how it works. Our programs. You can get all the vectors of the magnitudes here.
Yes. The videos are saved.
Yeah, exactly.
On a text file with all
which are here, the
X,
reports.
Y, Z component, velocity, acceleration, position, magnitude.
Everything, you can use it to work, whatever you want. So,
well, hope you like it.
Yeah, and I hope if you want the code, you can just use it. It's open code. We hope you've liked our presentation.
Yeah.
And thank you for hearing us. Goodbye.
Goodbye.